Hello and welcome to part 7 of this series on denotational design on affine functions. And so, as promised, I'm going to talk about the concept of law transfer. And to do that, I'm going to show you a module that I've written. I'll have a link to it in the description below. Now, this module's going to require a little bit of explanation. So the first thing I've done is define a record called raw monoid. You could also call this a lawless monoid. It's just the structure without the laws, okay? Is monoid, which we saw in the previous video, is the way you prove laws on this operation and this identity element. Okay. Then I've defined a record called monoid homomorphism, and it takes a few arguments. First, it takes a meaning function from type A to type B. It takes an equivalence relationship subscript 2, which is from B to beta set. And then it takes a raw monoid A and a raw monoid B as arguments. I'm going to skip this instance bit for now, and I'm going to skip the fields just for now, and I'm going to talk about this definition down here, which is the equivalence relation for type A. And this is the heart of law transfer, actually. So A, equivalence relation 1B, is defined to be the meaning of A is equivalent under equivalence relation 2 to the meaning of B. And if this is true, and type B is a monoid, then the laws, and also these two homomorphism properties are true up here, then the laws transfer from the second monoid on type B to the first monoid on type A. And the focus of this video will be looking at this particular function, which takes a proof that type B is a monoid and yields as a result a proof that type A is a monoid. So it's very important, when you're setting up this record, you have to fill in these two fields with two proofs that the meaning of the identity element on type A is equivalent under relation 2 to the identity element on type B, and also that this homomorphism property on the dot operator is also true. Now, you'll notice here that I'm using the same Greek epsilon here and here, and the same dot here and here, even though they're actually different operators. This dot has type A to A to A, whereas this dot has type B to B to B. And this was done with a very nice trick that I somehow managed to work out myself. And what I've done actually here is I've used this special syntax here, open raw monoid instance brackets, ... close instance brackets, public. And what that does is it brings into scope a slightly different version of this and this in its type signature, in which it expects a instance to be somehow in scope, and if so, it will fill it in. I guess I could show this right now by just going underscore set underscore equals question mark, and then what I can do is go, let's have a look at the type of this. So I'm going to press Control C D, and you'll see here over in this type signature that it's expecting a raw monoid instance, and then it gives you an opt2 A1. So if you have a raw monoid A1, then it gives you an opt2 A1. Well, that's really nice. So because I defined, so this record takes as an argument monoid A and monoid B, and then immediately afterwards I define instance of monoid A and monoid B, which means that both these things are in scope. And so now this particular syntax here can be overloaded, and Agda's smart enough to work out how to do this. In Haskell, this is simply type class resolution, but we don't call them type classes in Agda. All right, so I think now we're ready to actually have a look at this function isMonoid via homomorphism. So as I said, it takes a proof that type B is a monoid, and then it transfers the proof from the second monoid on type B to the one on type A. And we have to create one of those structures which we produced in the last video. So I have to fill in the isSemigroup and the identity fields. And I've done that, but I've left some holes, okay? So I'm really just going to gloss over what this whole is-equivalence, congruence stuff is all about. I will say one thing about congruence. So whenever you're using an equivalence relationship that is not propositional equality, then you need to define your own congruence laws in order to be able to do even basic proofs. And so this isMagma structure actually has a congruence field in it, and I think I'll show you the type of that. So it just says that it's congruent to on the operator dot, and then, well, this isn't really very helpful, is it, this definition? So I'll show you a little trick that I sometimes use. So what I'm going to do is I'm going to write up here underscore set equals question mark, and then what I'm going to do is actually type in congruent sub 2, and then I'm going to normalize this, and that's much more useful, isn't it? So it says, given an equivalence relation and one of these operators, and x, y, u, v are all of type A1, then if x is equivalent to y and u is equivalent to v, then x dot u is equivalent to y dot v. Well, that's what you would expect, and for a binary associative operator. So that's really nice, and that's basically all that is. And this proof's already been done for us. I did it earlier, but we'll just sort of have a look at it. Now, I've actually laid the proof out slightly differently to the way I have been in the previous videos. You might actually prefer this style because it's a little less visually cluttered. The reason why the meaning of x dot u is equal to the meaning of x dot the meaning of u is that, but it's off to the right, and perhaps that looks a bit visually less cluttered. So why is it true that the meaning of x dot u is equivalent to the meaning of x dot the meaning of u? Oh, well, that's just the homomorphism property that is actually an argument to this monoid homomorphism record. Okay, this is something that we provide to the record in order to do this law transfer. Then we simply apply this dot congruence to these two arguments which are provided up here to show that, and this is on the second equivalence relationship, so equivalence relationship subscript 2, the meaning of x dot meaning of u is equal to meaning of y dot meaning of v. And then we use the homomorphism law in reverse by using sim here to get back to y dot v, and there you go. We've transferred across congruence. That's really nice. And what we're now going to do is fill in the proofs for all of the other properties. So that's going to be left identity, right identity, and associativity. Now, what's really nice about these proofs is they're just completely straightforward. I mean, they're going to look something like this. There's really no thought involved. And the beautiful thing about this is you could do this for any mathematical structure. It doesn't just work for monoids. if you have any mathematical structure and you define a homomorphism on it, which again is something that can be done just by looking at the structure, and then you define the equivalence relationship subscript 1 so that the meaning, well, in the way that we've done it before, like this, then you'll get law transfer as well. So this is a general thing that you can do on any mathematical structure. So you would have to write one of these modules for each mathematical structure that you wanted it to be true for and sort of grind through the proofs, but they're all really, really straightforward. I don't know of any way that this could be generalized in Agda. Maybe some form of generic programming or something like that, but for the moment I think you just have to do it. So let's have a look at what we might want here. Okay, so I'm going to suggest that that this is going to be equivalent to this. Okay, which is quite nice. And that is merely an application of homo, which has 2 arguments, and that's applied to E and X. So that's done. And then the next thing we might want to say is that's just E, and that's meaning of X. And how can we say that this is true? Well, we can do this under the the epsilon homo property, but we're actually applying it just to the left-hand side of this dot. And so actually what we're going to use is Kong. It turns out that Kong has a left and a right form. So this is the left form. And let me just remove that for the moment. And okay, I've got an error there. Let's just have a think about this. It only takes 1 argument. That's why. Okay. So again, it's not liking this very much. I think I might be using the wrong one. I need the right version of it. Well, we'll be able to tell why when we have a look at it. Okay, so .cong r, I'll press meta dot now, and we'll see that its definition is right congruent. Let's not worry about, well, just look at this type, and that says that for all x, underscore dot x preserves equivalence. Okay, so it's named because the thing on the right doesn't change, I believe. Yes, it's a strange name for it. So basically it's just saying that this bit doesn't change. Okay. Anyway, so then what we have to do is apply epsilon homo here. I'll refine that, and that's done. That's great. And then we have epsilon dot meaning of x, and then we know from the fact that epsilon is a right identity, a left identity on the second equivalence relation that this is true. So we are simply going to apply the identity L property on, well, let's just refine that first. And what's going to be the argument to it? It's going to be the meaning of x. So that's done. And the proof for the right identity, it's going to be really, really similar. So let's just do that. Let's say meaning of x. Sorry. And then that's going to be homo x ge. Homo xe. Okay, let's define homo x. It says cannot refine. Oh, I've gone too far in one step. Reload, refine, lovely. And then the next line is going to be where we remove that. And this time we're going to use the other Cong property, which is Cong L. Reload, refine. And then finally, we're going to fill that in with identity R applied to the meaning of X. And that's the right identity done. And we only have one more thing to do, and that is a sock. This one's going to be a little bit more involved, but not a whole lot. So let's get going. I think the first thing we want to do is do the homomorphism at one level. Like that. And that's going to be homo applied to x dot y and z. That's gone through, that's lovely. And then the next thing we're going to want to do is perform it here. I'm not going to add brackets onto that since we know that dot associates to the left, and this is going to involve our old friend Cong. Since the right hand side is not changing, we're going to be applying that to just homo xy. Okay, I haven't quite got that right. Maybe I do need to put brackets around this. I can't quite work out in real time why I require those brackets. Perhaps you can work it out. And then I want to reassociate, and we are now in the domain of the second dot operator. This is the dot operator on types B, so we can just apply the associativity property. So it's going to be a sock. Yes, well, first let's write down the next line. So we want to reassociate it this way. Reload, refine, and now we have to apply that to 3 arguments. Well, I think that's going to be the meaning of x, the meaning of y, and the meaning of z. There we go. And now we're going to work backwards until we get back to the final thing. So the first thing we want to do is copy this line, and we want to fuse those two together, I think, into y, the meaning of y dot z. And the way we're going to do that, yeah, and I can take the brackets off already. That's really nice. So the way we're going to do that is by applying sim. So we're doing the reverse of what we did before, and then I'm going to use Cong L and then homo something something. Reload, refine, and the something is going to be y and z. Great. And then finally, we're going to turn it into this. And that is going to also require the use of sim. And it's just not going to require Kong, it's just going to require homo. And then the homo is applied to x and y.z. And beautiful, we have completed that proof. All right, so now you can see those proofs were really straightforward, and you can do this for any mathematical structure if you just set it up this way. I like to think of this as kind of a meta-mathematical property. You have a mathematical structure on something, you prove some laws on it, then you have a meaning function, and you define the equivalence relationship on the thing you want to transfer to it in the following way, like this, and then you can do law transfer. But you'll have to write a module, something like this. So you probably want to see this in action. So I'll just open up this module here. This is something I haven't shown you. It's something I prepared earlier. This here is where I actually go to the effort of proving that affine functions are a monoid under function addition and const 0q. So the dot is plus with the hole in it, that's function addition, and the identity element is const 0q, which is the function that returns 0 always, no matter what its argument is. And then I do some proofs on that, which you don't need to worry about. But here, I actually transfer the laws over. And I do this because equivalence is defined this way, which says that A is equivalent to B if the meaning of A is extensionally equivalent to B. Well, extensional equivalence is the second equivalence relationship here. And then we just simply apply this is monoid via homomorphism function, and we get back a proof that circle plus and 0q, 0q are a monoid. It's absolutely fantastic. So that actually concludes this series of videos for now. And thanks for watching.